turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists. This is the programme where we bring you the latest breakthroughs in science, technology and medicine and talk to the biggest movers and shakers in the field. With me, Chris Smith. And this week, teaching an old mine new tricks. Obsolete workings are being repurposed in the name of science.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Today, we're going to talk about mining, and not so much about modern day mining, but what we can do with the literally thousands of derelict or legacy mines that are left behind across the globe by the old timers from yesteryear. Because it turns out that some of these incredibly deep, incredibly hot, and incredibly well shielded environments, dating from, in some cases, hundreds of years ago, are actually the perfect places in which to site 21st century technologies. We'll learn about the system that turns old mine shafts into gravity batteries capable of powering towns, the project Deep Underground to detect dark matter and other exotic cosmic particles, and projects to clean up the environmental impacts of old mine workings. But first, to give us a sense of the scale of what lies beneath, here is Gavin Mudd, who's from the British Geological Survey.
If we look at the UK, we know that about 25% of homes actually sit above a former mine, most of which is coal. But in some areas, of course, we're looking at old tin mines, copper or lead mines, and so on as well. But certainly we see that same pattern globally.
And are they well documented? Do we know where they are?
In general, we know where they are. Often we don't necessarily have the production records, and each individual mine can range from anywhere from tens of tons of metal to sometimes tens of thousands of tons or more as well. Same as with coal, we can go from thousands of tons up to hundreds of millions of tons of coal, or even billions of tons of coal in some cases. So the scale can vary enormously.
And what sort of condition are these old workings in?
Yeah, condition can vary. We can see mines that nature has basically taken back over. We can see mines where there are still active issues that need to be very carefully managed, such as mine waters that can be acidic and carry trace metals that do provide risk to that local environment. Typically, I suppose that's the big question, is we need to understand what those sorts of risks are and work out how to manage mining and work out what the post-mining land use really becomes.
And I suppose it's not just the hole in the ground, it's the stuff that's come up with the stuff we wanted that got discarded and turned into a spoil heap. That's also a problem sitting there.
Mining is pretty simple in some ways. We dig the rock out of the ground that contains either the metal or the minerals that we're after. And then to get that rock, we also need to dig out other rock or other sediment. Let's just say it's 5% copper contained in the rock that you're processing. In mining, that would be called ore, but you've got 95% is therefore not copper, and that's basically left behind as a solid waste, or what we call tailings. And so that tailings has grown over time, and as mines have got bigger and bigger, the grades have declined. So now we're not chasing copper that's 5 or 10%. We're chasing copper that's 0.5%, and in some parts of the world, even as low as 0.2%. So in order to produce more and more copper, we need to mine more and more material all the time. And this is why modern mines are typically much, much bigger, whereas your older mines, pre-20th century, typically were much smaller. And so that's one of the key distinctions that I think we always need to be, mindful of.
Double-edged sword, this, in some respects, isn't it? Because I remember talking to a colleague of mine in South Africa. I went to visit one of their gold mines, and they showed me their spoil heap there, and they had billions of tons of material they'd been told to sort out. But they pointed out that the old-timers had much less good technology than we do today. So, in fact, rather than dig up fresh stuff, you go digging up the tailings, because you can get much more out of that with a higher yield with new technology than you could ever get out of the ground these days.
Yeah, if you look at the Witwatersrand Basin in South Africa, typically mining anywhere from, in the early days, it was 30 grams per tonne or an ounce of gold per tonne of rock they processed to get the gold out of. And an operating mine these days would be 5 grams per tonne there. The tailings would still be 0.5 grams per tonne. Now, when you look at many gold mines around the world, the average globally is around about 1 gram per tonne. So if you don't have to pay the costs of actually digging the rock out of the ground, and all you have to do is basically get it from the tailings dam or that mountain of residue into a process plant, you're basically going to pay half the cost kind of thing. You only have to pay for the processing cost and not the mining cost as well. For South Africa, the other issue is uranium. There's residual uranium in that tailings as well. But sometimes we also think about it and saying, well, the old timers were very efficient in terms of the way they mined and processed with the technology they had, but they didn't think about environmental issues or the longer term environmental risks. And so sometimes going in and reprocessing old tailings, you can actually re-engineer where they're placed, clean up that site and get the environment into a much healthier, more sustainable sort of condition as well. That could be a really important part of the overall reasons to go back and have another go.
So that's one way that we can give an old mine a new lease of life. We can go and clean up the mess that was made, perhaps even making it pay for itself in the process. What other opportunities are there for some of this legacy mine workings that we have in countries like the UK, old world economies? What can we do with, and what are people trying to do with those old mine workings?
Old mine working can be, I suppose, thought of in all sorts of ways. You can use the workings as a kind of pumped hydro scheme, so using gravity as a way to store energy. Technically challenging, but it can actually work. And there's certainly, I've seen some work at mining regions around the world where that type of technology has actually been used historically, in the old hydraulic days, I guess. The other thing we can do is convert it into things like country parks. So you basically recontour the surface, make everything safe, and then you can reuse that land either for recreation. In some places, you might even be able to build houses. Another idea would be, especially with quarries, for example, make those old quarries lakes. So you've got a big hole in the ground. There's always lots of water here in the UK, so fill that hole with water, and then you've got a lake that could be used for various things as well. There's some of the main ideas, or like we've seen with the Eden project, you build basically a large sort of centre in the middle of it, and that way you get a great functional venue that you can use for all sorts of things.
And are people turning old closed down mines back into mines again? Because I did read somewhere that, for instance, some of the old tin mines in Cornwall, where initially they were going for things like copper and tin, there were things like lithium down there as well, but they didn't know they wanted that at the time. Now that's incredibly valuable.
One of the things that I think is different these days is we don't just look at the singular metal, the sole mineral that's of interest. We think about everything that's there and what's possible. So with some of the projects in Cornwall, for example, we're looking at not only at just the elements that are there, such as lithium or tin and copper, but also things like the heat. Right? If we're going deep into the earth, we know that there is heat stored there. Can we use that geothermal energy as part of the way to actually power the mine? We're not only providing the minerals that we need for modern technologies like lithium, but also the challenges that we have to face in terms of climate change and reaching net zero emissions, already building into that mine and making sure we get the most out of everything that we do. There's a lot of effort down in Cornwall to build those sort of 21st century style mining projects.
Gavin Mudd at the British Geological Survey there. Mines supply metals that are vital for everyday objects like cars and smartphones, but as Gavin was just saying, once mines are abandoned, the waste left behind means that traces of the metals and minerals that were being sought can seep into the water and soil that surround the site. In parts of the world where industry meets agriculture, that can make growing crops problematic and have onward consequences for human health too. This was the case for a former gold and copper mine in the Philippines, which was abandoned in 1982. The mine had no significant formal rehabilitation program in place, but Indigenous people now live and farm in the area. So how has this been done? Well, my colleague James Titko went to meet Anne Jungblut from the Natural History Museum, who's been involved in the BioPlusMine project.
Our project, BioPlusMine, is centered around a community called Santo Nino in northern Luzon in the Philippines. It's on 1,300 meters in the mountains, so it's a little bit more cooler there than like in the middle of Manila. Hilly, forested environment. And there was the copper mine that was closed in the 80s. It was an open pit mine, so basically they just removed the surface of the earth, and then they created waste dumps where they left the mine waste. And this community is on ancestral land of the indigenous people. And so there it's an area where communities have lived for many generations, and they're still now living in that area where the former mine site was.
Can you give me an idea of the scale of the number of legacy mines we see around the world? Is this a problem in all countries, or is it concentrated in particular economies?
So there are legacy mines around the world. And for example, in our project in the Philippines, they have now recognized there are more than 20 legacy mines. And part of it is also in the past there was less legislation. There was less regulation for the companies to do a rehabilitation, renaturation of the sites. But with more and more guidelines in place, the number of legacy mines that will be created in the future will be a lot less.
So that's a positive solution for reducing the number of legacy mines that might come to exist, but that we're still stuck with the ones that do exist. Can you give me some examples of the cutting edge ways in which you're assessing these sites?
So options are, for example, like drone technology, so that allows us to image large areas across kilometers of site, 3D, like the amount of vegetation, how much plants, are there areas where there are no plants, is that a risk that there could be rockfall? Drone technology, remote sensing is very, very important. We also think DNA sequencing is very important because we can use free DNA in the water to track what is the biodiversity, how many species, and potentially find indicator species using DNA sequencing. I am an environmental microbiologist, so my role was particular to study the microbiology in the soil and the water. A really striking result was that we found that the soil microbiology in the sites where there was the highest copper was very different to sites where the agriculture was happening and the local forests. And I thought that was very striking because microbes are very small, they grow really quickly, they can change super fast, but even after 30 years, the soil microbe was really different. And we also found, say, microbes that are more common for environments where there is a lot of geochemical, like chemistry happening. So that was actually very striking. And I've worked in the tropics and the polar regions and really didn't expect that result. So that sort of shows even if something is green on the top, it might actually be, there is still a signal of this impact.
That is a very interesting finding. So using all the data you've collected and all the harms you identified, what have been the consequences? What have been the actions that have led to change for the benefit of that community?
So the first thing was we've established what were the biggest concerns for the local communities. That was access to water and in parts the agriculture. And so we're working on, at the moment, experimental level, small-scale water treatments to, for example, to remove the copper and increase the pH to make the water usable to some extent.
How transferable will be the techniques that you've pioneered here for other legacy mines around the world?
Yeah, so we're hoping that this small project potentially be able to help in a larger way to potentially be a blueprint or create a framework to how we maybe do biodiversity assessment, identify with the community how has the mining affected, what interventions are needed.
Anne Youngblood there in conversation with James Titko.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith, and this week we are looking at the legacy of old mines left over from yesteryear, including giving some of them entirely new roles. On the way, how a former gold mine is helping us to probe the fabric of the universe. But first, to a clever approach to turning abandoned mine shafts into energy storage systems. As the world shifts towards renewables, sources like wind and solar are playing a huge role. But the problem intrinsic to these technologies is that they're intermittent, meaning that we need an effective way to store the surplus energy that they provide for the times when the sun doesn't shine and the wind doesn't blow. Traditional batteries are one way to do this, but they're very expensive, they have an environmental impact, and they can catch fire in some cases. So step forward, gravitricity. The clue's in their name. They use gravity to store electricity as gravitational potential energy by hoisting a huge weight to the top of a mine shaft. When you want the energy back, you drop the weight and the lifting gear becomes a generator. To talk us through it, here's Gravitricity's Chris Yendall.
If you are to look at a mine shaft, the vertical drop there can be substantial. In some cases, several kilometers from top to bottom. And this system ultimately stores electricity by raising a weight and converting that into a potential energy. When the system wants to give electricity back to an electricity grid, for example, the weight can be lowered. Now, it's attached via cables to electric winches. The winches effectively become generators that spin and generate electricity from that gravitational pull to put the electricity back onto the grid.
It's a bit like, I suppose, if you've got a long case clock and you winch the weights up with those chains, they go up to the top and then they are effectively powering the clock, aren't they? As they fall under gravity, they're making the clock tick. You're doing something sort of similar.
That's exactly it, yeah. It's the same technology that one might find in a very old grandfather clock. It's applying that same physics, that same concept to a challenge that is arising today, which is providing energy storage to sit alongside the likes of intermittent renewable electricity generation technologies.
That was going to be my question to you, Chris, which is what problem does this actually address? Why do we need this?
When I started my working life, I was actually working to deploy wind turbines, and I'm fascinated by them, significant structures generating electricity from a free fuel, shall we say. So that's very exciting. But what happens when the wind doesn't blow? There's a gap. And I don't know that we are so comfortable, especially in the developed world, with intermittent electricity supplies. So what do we do when the wind doesn't blow or the sun doesn't shine for solar panels? We need to store electricity when we can make lots of it, and then use that when there is times of demand and less available clean generating technologies.
I need you to appeal to my inner geek now and wow me out with the sorts of scale that you're talking about. You mentioned some mines are kilometres deep, but how much mass, how heavy are the weights you're deploying, and therefore how much energy can one of your systems store?
We have found suppliers that are lifting in excess of 10,000 tons in a single lift. That's an awful lot of weight. That kind of value would be well over, let's say, 50 blue whales. At this stage, as we develop the technology, we're not quite lifting that many, but we are looking at lifting or lowering one after the other many weights so that the total mass, if you like, in a system could be well in excess of the 50 blue whales that I'm talking about here. Electricity grids typically see periods of several hours of demand. So this is a system that caters to that. Any one mine shaft might offer 2 up to 8 megawatts of power. To contextualize that, that's 2,000 to 8,000 homes being powered by this repurposed mine site.
I suppose one of its major strengths is that, it's a very simple concept, but it's instantly on. Even with some of these pump storage systems where you let water flow down a turbine, there's still a ramp-up time. This must be incredibly responsive, very, very quick. You need that surge and you can switch this on.
Absolutely. As a company, we're in the stage of starting to prepare early projects to repurpose real mines that are coming to the end of service life and have that need. In advance of that, and a key part of developing any new technology is a demonstration of that. So for us, what that looked like was a smaller grid-connected system which was actually situated down on the docks here in Edinburgh, where our headquarters is. The exciting outcome of that was a response time of less than 1 second. So when some kind of grid control center thinks, okay, we're light on power here. We need more in the system. And we were able to prove that within 1 second, we could reply to such a signal to be operating at full power and helping to balance that electricity grid.
Is it also beneficial that a lot of our major cities, certainly in countries like the UK, are sitting on top of mine workings? That's why the city is there in the first place. And therefore, you are minimising the grid transport cost of sending the electricity over long distances because you're feeding it onto the grid near where it's actually going to be consumed.
Yes, typically mining infrastructure has been set up around towns. So there's that. On, I guess, the more business side of things, we're starting to think a lot about, well, how many mines are there in the world and where are there mines that are looking for something else to do right at this point in time?
So how big do you think the potential market is for this?
Oof. In the UK, we spoke with the Coal Authority, which has the ultimate responsibility to look after a lot of legacy mines in the UK. They have records for over 50,000 vertical shafts in the UK alone. Now, that's a phenomenal number. And I think our view on that is not all shafts will be suitable for a plug and play gravity-based energy storage system, shall we say. But if you think about that number in the UK alone, then you look at other geographical areas, the potential, pardon my pun, feels very great. It is also very interesting to us at what stage a mine is. So in the UK, a lot of our mine shafts closed many tens of years ago. And so we're starting to work around, well, what do we need to do to open up those mine shafts? A lot have been backfilled, but many have also just had a lid put on top, if you like, a cap. Of importance to our process is how to prepare the mine shaft ready for the installation of such a system. That has led us to mine owners who are facing this challenge now, where they are approaching the end of service life and think, well, there's a really significant asset that has already been built. Can that be repurposed to provide another use case? So I expect that a lot of our early systems will deploy in mines that are coming out of service right as we speak.
What's the position on ownership of the electricity? Who owns the underground facility? Because this isn't exploiting a mineral. This is a different use for the mine. So where do we stand legally on doing this?
Yeah, that is interesting, isn't it? The way that we're thinking about it at the minute is ultimately the system attaches to and is developed on land at surface. The legal status of it could, in theory, be relatively straightforward. It might appear something like a land use lease. In terms of who owns the electricity or who's responsible for that, I guess there's two ways in which a system might be deployed. In one sense, the mine owner might have the asset and they would look to trade electricity storage services with the electricity grid operator. The other way of thinking about it is any kind of system could also help to ease the load locally on site. So, for example, an industrial process that had a very peaky requirement for power on site might be able to use this storage solution to alleviate any stress or any additional power import requirements that they may have traditionally looked to the wider grid to deliver.
I was going to say it might make mining itself more viable for the mines because it gives them another revenue stream and offset some of their direct costs, which might make the difference between a mine staying open or not being viable at all.
Yeah, absolutely. And you can go even further into that in that when mines come to the end of service life, even though they have finished mining, in order to maintain sufficient level of environmental consideration, in order to ensure that there's no environmental impacts after the mining has occurred, they may even have requirements to retain a mine shaft in place for many years beyond. So in that case, this is something that can provide a useful service in the energy transition, as well as easing the financial headache for the owner of that mine shaft.
It's a great idea, isn't it? Chris Yendall there from Gravitricity. Well, finally, we're going to take you to the Samford Underground Research Facility in South Dakota, which used to be at the heart of gold mining in the United States. The mine has since been repurposed as a world-class science facility in a bid to help researchers from a host of fields, including physics, biology, geology, engineering, and even education. Here's Dr. Jarrett Heiss, who's the science director at the Samford Underground Research Facility.
I'm sitting in Lead, South Dakota, on the western edge of the state, in the geographic center of the United States, where Starting in 1876, gold mining was the name of the game. And for 125 years, that was the main industry in this town, in this area. Over 40 million ounces of gold was extracted from this, the largest gold mine in the Western Hemisphere. And we have been fortunate to inherit this fabulous resource and are now dedicating it as a science laboratory for various science disciplines.
Is it a vertical shaft? What's the anatomy of the mine, as it were?
Yeah, the main access underground is via two main shafts. They're named for former mining superintendents, the Yates shaft and the Ross shaft. Equally important is how we are able to ventilate the underground workings, and we have two principal ventilation shafts with large fans on the end to suck air down those two personnel shafts to bring, 500,000 cubic feet per minute into the underground spaces.
And how deep is it?
The facility extends all the way to about 2.4 kilometers or 8,000 feet. Right now, we are only able to access down to about 5,000 feet or a little over 1.5 kilometers with the Yates and Ross shafts. To go to the deeper sections, you would need internal shafts called winzes. And some of the lower elevations of our facility continue to be underwater, and we don't have the shafts to the deeper areas refurbished to allow us to gain access to the 8,000 foot level.
Does it get hot down there?
It does. On the 4,850 foot level, which is our main level for physics and other disciplines, the rock temperature is around 30 degrees Celsius. And all the way down at the bottom of the facility, 8,000 feet or 2.4 kilometers, the rock temperature is over 50 degrees Celsius.
So what attracted you there in the first place? Why would a bunch of physicists and geologists and biologists want to go down a massive deep hole?
Lots of good reasons. I'm glad you asked. There are a number of unique attributes at our facility that attract researchers from a host of disciplines. For physics, it's the fact that we are a deep site with a rock overburden that shields cosmic ray muons. On the surface of the Earth, if you hold out your hand, 3 cosmic ray muons are going through your hand every second. On the 4,850 foot level, or 1.4 kilometers below the surface, that flux that was 3 per second translates to 1 per month. And if you're a physics researcher exploring very rare processes, searching for dark matter, discovering properties of neutrinos, then that affords you a very quiet environment to do those studies.
Is that what you're looking for?
Yeah, one of our premier physics experiments, called the Lux Zeppelin experiment, is in fact searching for evidence of dark matter. They are using 10 tons of xenon looking for collisions with WIMP dark matter. Now, a WIMP is a weakly interacting massive particle, a special category of candidates for dark matter in our universe. And the collaboration just earlier this week updated their results and have demonstrated that they are, once again, the most sensitive experiment anywhere in the world looking for this type of dark matter.
What are they actually looking for then? What does the xenon do, and how does it tell us whether dark matter's there?
Sure. So in this quiet environment on the 4,850 foot level, they have essentially a thermos inside a large ultra pure water shielding tank to make a very quiet environment. They're looking for light signatures, energy deposition, as a WIMP particle interacts with the nucleus of the xenon atom, producing light. And that signature of light can be distinguished from more natural and more well-known types of backgrounds, like a beta decay or a gamma ray particle.
You mentioned that it's not just particle physics that's going on here. There's a lot of engineering type stuff happening as well as geology and even biology. So what are those other projects that you've got going on down your mine then?
Yeah, I'm glad you asked. We have in total about 30 different experiments taking advantage of our facility. Some involve large collaborations, mostly on the physics experiment side, but there are a number of smaller groups in the biology, geology, and engineering disciplines that are also taking advantage of SURF. Just a couple examples. One group was funded by NASA as part of their search for life on other planets. And so they were doing some research and development at our facility with instruments that were taken to Mars on the 2020 mission. So they were testing instruments that characterize the rock and could help analyze for signs of life on another planet on Earth in our facility.
And Jarrett, do any of your scientists ever slope off and you notice them kind of tapping on the walls, or they've got their pickaxe strapped to their back and they're kind of...
No, yeah, they don't stray too far from, and certainly the physicists don't stray too far from the clean labs that we operate, because that's where we have the Wi-Fi and the espresso, which are crucial ingredients for science. And not only that, but it's well known, and we explain this to the researchers here now as well, is the areas where we have the science caverns are very far away from the mined areas where the gold was deposited. And today those areas are not very stable, because when they extracted the ore and the mineral, they weren't anticipating, or they didn't care to have those sites used and accessible for decades into the future. They wanted to get in just long enough to get the gold out and then move on to the next area.
So the only gold in them their hills these days is the gold blend in the coffee machine. An incredible lure for scientists. Jarrett Heiss there, who's the science director at the Samford Underground Research Facility. So there you have it, mines that have been around for hundreds of years, still helping in the modern era to explore the cutting edge of science. Well, that's it for this week. Next time, we're going to be taking a closer look at the appendix, the organ that we often chop out with abandon. Is it actually a lot more useful than we first thought? The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the team, thanks for listening, and until next time, goodbye.